Hello, good morning, good afternoon. My name is Justin McCright. I'm with BP in the DataWorks Innovation and Engineering Organization. So today I'll be giving you a technical presentation leveraging IoT big data to bring insights to global vessel patterns. So the organization for today's presentation, I'll start off with giving an intro to BP's OneMap and OneMap Live platforms. From there, we'll go into a discussion about how we've used FME in leveraging IoT big data to create some vessel density products. There'll be three main challenges that we'll talk through and how FME helps solve those challenges, and then finish up with a business impact and questions and answers. All right, so what is OneMap? So OneMap is BP's enterprise geospatial platform for providing desktop, mobile, database, web, and other technologies to all BP functions. The OneMap platform is available to anyone in BP and is used for viewing, analyzing, and sharing all types of spatial and non-spatial data together. Currently, the OneMap platform has over 25,000 users across 30 plus portals, and these portals service a multifunctional base of users. Most of these portals are separated by geographic regions, but we also have some functional specific sites for groups such as retail, refining, and weather. OneMap is not just about analysis of maps, though. This really encompasses our data management tools and practices as well. So across these portals, we currently have over 76,000 datasets available to our users. The majority of these datasets are regional and are functional specific, and those datasets are managed locally by geospatial professionals or by the users themselves. However, there are a portion of these datasets that are centrally managed and collaborated across all these portals, and this is where FME really finds its core value for organization. So FME gives us the ability to connect to a highly diverse set of datasets and formats across all internal regions, functions, as well as external datasets. And this allows us to easily transform, standardize, and organize these datasets into a central location. Additionally, FME Server helps supplements this and gives us the efficiencies and acts as an easy-to-use platform for managing our automated workflows. So OneMap Live is an extension to the OneMap platform and is for capturing a variety of technologies that we use to collect, manage, and analyze moving assets. So the goal here is to leverage IoT data to derive location-based knowledge for addressing business problems. So not only are we providing real-time geospatial asset tracking, but building on those streams with geospatial analytics. This is a big deal for BP and a lot of interest in this. I would imagine that this is also a big topic for other energy companies and probably companies outside of the oil and gas energy field as well. By the end of 2020, 200 billion devices are expected to be connected to the Internet of Things. So these devices will provide organizations that are equipped to leverage this volume and velocity of the data with the massive efficiency gains and clear competitive advantage. So as I said, BP's really big into this right now. And OneMap Live helps answers a lot of the questions that the business is coming to us to help solve. So the OneMap Live is a blend of that geospatial analytics and visualizations in combination with big data IoT. Today, this is being leveraged across BP for global and regional specific monitoring of our assets. And this really gives our users a lens to better understand our operations and helps to drive efficiencies and competitive intelligence. So we move into a very specific piece of the IoT big data and focus in on vessel data, specifically AIS, or Automatic Identification System. We're currently collecting the geospatial location and ship information for over 500,000 vessels worldwide every 2 to 3 minutes. So since OneMap Live's inception at BP in 2016, we've collected over 20 billion points, just to put it into perspective. So two functional questions here with this amount of data is one, how can we transform historical AIS positions to visualize patterns? And then how can we expand on that to view these patterns and understand how they evolve over a day, week, month, even over a year? So there'll be three main challenges to help answer these questions. The first being extracting data and aggregation of records. The second being workflow execution and efficiency, and then following up with a automation. Right, so challenge one, extracting data and aggregation of records. So at BP, we currently leverage Elasticsearch as our big data IoT solution, which allows us to leverage query capabilities such as geohash grid aggregation and geocentroid aggregation. So I'll spend a little time talking about these two query capabilities because they're pretty foundational to the remainder of the presentation and basically how we've managed to use FME to help solve these challenges. So the geohashing is a hierarchical spatial data structure which groups points into buckets that represent cells on a grid. So each grid in this system represents a geographic location and is labeled with a short string of letters and digits to give that geohash a unique ID. Geohashes covering a large area, which are referred to as having low precision, will have a short unique ID. And the inverse of that, geohashes representing a smaller geographic region will have a high precision and will have a unique ID with several letters and digits. So in practice, specifically for working with historical vessel AIS data, so the geohash grid aggregation query returns a geohash ID with an associated record count representing the amount of vessel pings in that geographic region over a specified amount of time. It's important to note here that increasing the geohash precision can be costly in terms of this database querying and computation time. Elasticsearch supports up to a precision level of 12, which covers less than a square meter. So there really needs to be a considerable consideration to find an optimal balance between the appropriate geohash precision and the span of time. So in other words, if your aggregation can take quite a bit of time, if you're looking to get a high precision for all the records for over a year. For this analysis, we'll be using precision 5, 6, and 8, but I'll talk more about that in the workflow efficiency section. So moving on to geocentroid aggregation. So this is in a supplement, the geohash grid aggregation. The geocentroid aggregation computes the weighted centroid from all the coordinate values within a geohash. So in other words, this aggregation will gather all of the record locations for a specified time within a geohash and return back a specific lat long that's influenced by the clustering of all the points within that geohash. So in practice, putting these two together, we first select a geohash precision for aggregating the historical points that best fits the particular span of time that we're interested in. We'll then utilize the geocentroid aggregation to ultimately have a single record that represents the amount of vessel traffic at a specific geographic location over a span of time. So the main takeaway here is that we're leveraging the database query capabilities, and by doing that, we've effectively largely reduced the amount of records that we have to deal with further down the chain of analysis. So challenge 2, workflow execution efficiency. So as I mentioned, we use Elasticsearch, and querying Elasticsearch is done via an API. So the first question here is, how do we overcome the hurdle of a 10,000 record limit that's typical of an API? Second question, how can we deliver a timely product that allows users to understand these patterns of vessel movements globally and locally? So timely being, how do we keep this up to date regularly? And then third, how do we quickly convert these results into a compelling product that is performant in OneMap? So question 1 of challenge 2, how do we overcome that API limit of 10,000 record limit? So best practice for APIs is to not return more than 10,000 records. There are some complex ways to get around this, but typically it's best practice to work within these limits. And this just prevents system disruptions and ensures equal distribution of resources across the system. So to handle this record limit, we'll utilize a series of database queries and workflow tests to quickly move through regions with low vessel traffic and focus computation time on areas with high vessel traffic. I guess it's worth saying here that we could just do a baseline query to Elasticsearch to give us all aggregated records for precision level 5, and ultimately that would work. Although there would be a lot of resources spent in processing time on geohashes that contain very little vessel traffic. So this is a spot where we recognize that there is some opportunity to add some processing efficiencies into the workflow to save some time. All right, so how does this work? So starting with a low precision geohash in step 1, we'll make a database query to only return a count of the records within a geohash. So the idea here is to identify large chunks of areas where there is relatively low amount of vessel traffic. And that way we can process these areas first at a lower precision. If the larger geohash has less than 10,000 records, then we can be pretty certain that the higher precision geohashes will be less than 10,000 as well. Step 2 will test if indeed the geohash has more than 10,000 records. If not, the geohash will move to step 3, where we will actually execute the database query to return aggregation results and pass that further down the workflow. Step 4 is an anomaly check, capturing the geohashes that are just over the line of 10,000 record limits. And sometimes this just happens when making a call through an API where you get these records that are just right on the fringe. So these records will be passed back down to step 5, where they'll be paired to run through the full chain of workflow at a higher precision. Step 5 and 6 involves breaking up the larger geohashes into the next higher precision tier, and those will be run through the process again. So step 5 will query the database for a list of geohash IDs that fall within the larger geohash, and then step 6 will fragment that out as a JSON response to prepare for the next round. We do have some fail-safes in here to built in for handling any potential server timeouts or incomplete requests to the database. And sometimes it just happens through either some random network issues or server-side hiccups. So these fail-safes here just ensure continuity in the workflow and make sure that we don't lose any data along the way. So that's a real high-level look at the workflow. And ultimately, like, the takeaway here is that by using FME for this process, we're able to modularize each of these iterations to quickly replicate the process all the way through to the target precision that we desire. So question 2 of challenge 2, how do we deliver a timely product that allows users to understand the patterns of vessel movements globally and locally? The challenge here is to create a product that offers a balance between geographic coverage and granularity of the data set where it's needed most. Although we would love to give a global data set with a high precision, and ultimately we probably could, but we did decide it was better to provide a data set that we could process in a timely manner and still provide adequate coverage and detail in the areas that we needed the most. So to do this, we've created 3 separate data sets, global, regional, and asset views. The global view obviously will have maximum coverage, but will also have the lowest precision. On the inverse of that, the asset view will have only a targeted coverage of a region and will provide the highest detail or the highest precision for that specific area. So again, the goal here is to create a relationship between the coverage, geographic coverage, and the precision, and is really to maintain a positive user experience while improving and optimizing the workflow duration. So for perspective on these precisions, the global geohash will be run at precision 5, which covers approximately 5 kilometers by 5 kilometers near the equator. These dimensions will vary with latitude, obviously, but the regional views are run with a precision level 6 and have a dimension of approximately 1.2 kilometers by 610 meters at the equator. And then finally, precision 8 for our asset views with a grid dimension of 38 by 19 meters at the equator. The regional and asset views, we've decided those locations in particular for coverage over areas of BP's current operations. So in terms of the workflow, this is executed in a 2-fold approach. For the regional and asset runs, the job will begin with a specified list of geohashes covering the targeted regions. In addition to that, rather than starting at a precision 1, these jobs will begin the iteration at either precision 2 for the region or precision 3 for the asset view. And this again just builds on the workflow optimizations that we created for handling the 10,000 record limit. So question 3 of challenge 2, how do we quickly convert the results into a compelling product? that is performant in one map. So the challenge here is focus on the backend workflow. Now, at this point, we now have a full record list of lat longs and its associated density counts, and we now want to create a map product that tells a story. So the clear choice here for us is to convert this tabular data into a raster or grid file. And this effectively allows us to easily represent the scale of the vessel traffic across global regions and assets. But just as important, it's also performant as a layer in one map. So to do this, we first have FME dump the aggregated records out of memory into a CSV file. And there's two reasons for this. First, FME is really great at reading and writing CSVs. So we can leverage FME strengths here to not only catalog and save the process records to a CSV, but this also sets us up for reason two. So the second reason for writing to a CSV is to give us the ability to leverage Python to further increase the processing speed and transformation of these points. With Python, we can we can convert this tabular data into spatial data and then write these points to a staging feature class. From there, we'll use Python again, and we can utilize the ArcPy libraries to create our final raster product. I think it's worth noting here that FME can handle the portions in this workflow that we've elected to use Python. In development, we found that the Python was faster and did give us better options specifically for raster creation. So challenge 3, automation. So at this stage, we have a workflow that queries our big data database, aggregates the data into a map layer format, and then we have a product that tells us a story and is easy to use. So now we have to figure out how to best automate this process to keep these up to date. As I mentioned before, we'll utilize FME Server for this operation, specifically the workflows. And so rather than creating a separate job for each view and time span, we built the highly parameterized workflow that enables us to manage a single job and can process all the iterations. The FME workflow itself utilizes a parameter setup where key inputs such as precision values, geographic coverage, and time span can be easily swapped out at runtime. On FME Server, we string these together with the same FME script, but with just slightly different parameters to streamline the creation of rasters geographically and temporally. We do maintain, however, a segmented schedule for the datasets covering a longer span of time, and that's just because these take much longer to complete. So the past day and past 7 days are updated every day. Past 30-day products are updated every 2 weeks, and then 90 and 365-day products updated once a month. We did elect to not produce rasters for the 90-day and 365-day at the regional and asset, and that's just purely because of processing time. However, as computing gets faster and we get to leverage more technology, we may be able to do this and have it complete within a reasonable amount of time. All right, so let's take a look at these. So we're going to start with the global view at 1 day. So it's really interesting to kind of click through these and just see how the patterns start to appear and really starts to tell a story of sort of the core shipping channels that are used around the world. So all the way up to global vessel density of 1 year. Moving on to the region, so this is in the North Sea. Again, only have 1, 7, and 30 days here. We'll not have the 90 or 365-day, but again, you really can see the core shipping channels within this area. It's worth noting here that these products are only as good as the data that you have to work with, right? This is all contingent on having good AIS coverage, and in this particular area in the middle of the North Sea, you can see there's quite a bit of black there, and that's just purely because the AIS coverage is just not great there. You're further away from any particular sensors inland, and so your coverage is just not as great there. Looking off of the coast of Louisiana and the Gulf of Mexico and highlighting our 4 main platforms off there, and also added the pipelines in blue for context. So starting with 1 day and then moving through to 7-day and 30-day. This particular one can be pretty interesting as well. Sometimes you can see some seismic survey campaigns, and those become pretty obvious, especially on a 30-day look. All right, so business impacts and next steps. So, in terms of business impact, this data is critical for SimOps planning, simultaneous operations. So this allows our engineers to take a deep dive into vessel activity around a site of interest and potentially use this product for locating new areas for a potential platform offshore. And this also helps reduce chances of possible collisions or other vessel-related emergencies. Of course, there's some competitive intelligence that we can derive through identifying obvious vessel activities, as I said, such as seismic surveys. Um, Other potential uses could include understanding vessel activity at global and regional shipping channels, and this could help us with logistics and planning. And ultimately, to be honest, this is a great marketing tool for us. This really tells a great story of what the OneMap Live product is and what the geospatial team is capable of producing with that data set. So within the team, we intend on using the knowledge we've learned from this product to look at creating separate products focused on specific vessel types, such as seismic or commodity transport vessels. Capturing a rolling history of these products could potentially help us understand changes over time. Perhaps there are some changes in the shipping channels by season. And then finally, looking into how we can derive industry intelligence through something like change detection analysis. First thought here, again, we could use raster change detection workflows to quickly identify areas of seismic acquisition activities. But again, there are certainly more use cases within the same vein. So thanks again for joining. My name is Justin McCride. I hope you found this informative and interesting. And I look forward to answering any questions you have. Thanks.